And I'd like to introduce our next speaker, which is Andres Almasi from Telecom Paris Tech, as he's talking about video implanting, challenges and perspectives on probabilistic model of natural images and videos. Andreas.
Now you should and you should hear me well. Okay. So I'd like to thank Carola and Jean-Lip and the organizers for giving me this opportunity. It's really nice to be in Cambridge. And so I would like to talk about the work of my my former PhD student, Alistair Newson, on video and painting, and take the chance to, if we have the time, to talk about some perspectives on the subject. So, what's video in painting? It's the problem of, or the more traditional problem of image in painting is the problem of removing an undesirable object from a scene that you can mark by hand and create some image that is plausible and that fills in that region. So that after we remove that object, to see what should be behind, even if this is not restoration in the strict sense. It should be only plausible. It should not be exactly what was behind. And this is used in many applications, like in post-production of films and restoring older films and things like that. So to give you a grasp of the problem, we say that image in painting is well done when you look at the video and you don't see any artifacts. So in this video, I'm going to ask you to tell me if you see any artifacts. Lots of reflections? Where?
In the glass.
In the glass.
Behind, yeah.
There's even one reflection that shouldn't be there, right? So actually, that was an error. The original video actually had that one person passing through, and this person was marked to be removed, but its reflection on the glass was not. So, well. The point is that you don't realize when you look at the Inpainted video, apart from this artifact, you don't realize. So the motion is well captured. So you see the guitar playing, and that's the point. You should build a plausible reconstruction. This was done with the software I will present here, and that you can download from our site. So, what are the challenges in painting? So, this is an evolution of the image in painting that started in the year 2000, more or less. Well, the main concern was to, given an occlusion that was marked on the image, be able to fill in the geometric structures. That was the first concern of the early works of Masnou and Morel and Bartolomeo and collaborators. The second problem, it was more related to texture synthesis. So, given a small part of a texture, be able to resynthesize different versions of the same kind of texture in a larger region and use that to paint. Then the next point was to, of course, to bring both worlds together and to fill in the geometry, so the boundaries of this region, and then do some kind of texture synthesis conditional to that geometry that was filled in. So you see the discipline gain in complexity. In the case of video in painting, we have additional challenges and difficulties, namely, as Pablo Arias mentioned before and the previous speakers, you have to deal with the temporal consistency. So you cannot just treat one frame at a time. You have to treat the whole sequence as a whole object. You have to deal with dynamic geometry. That means objects moving, like in this sequence. So you have people walking, and at a certain point you have to reconstruct the motion of these people. So that's what we would call dynamic shape or dynamic geometry. But you also need to reconstruct dynamic texture, like water pouring or flowing or flames. So it's there are sort of 2D texture features that have also a particular spatial-temporal behavior. And then you have to deal with simultaneous foreground and background reconstruction. Foreground and background have most often different characteristics of texture, and you have to manage to reconstruct them both independently and avoid problems in the frontier between objects. And the main problem is that, well, those algorithms take very, very long to run, and that was an issue. So that was mainly the point that prevented, for instance, the algorithm of Wechsler about more than 7 years ago to become that mainstream, because it really took several days to run. So, what the algorithm I will present for image inpainting, for video inpainting, it is based on a very simple example-based or patch-based method, very similar to the work of Wechsler for video inpainting and the formalization given in the context of images by Arias and collaborators. But that was restricted to the case of image inpainting. But so this theoretical framework, which is very simple and very easy to manage, actually needs several key ingredients to make it really work in the case of videos. I will go through a few of these, but well, I will not detail all the subjects. Maybe in the questions if you want. So you really need to deal with spatial temporal patches, get a good minimization scheme to make it go faster, fast search mechanisms for corresponding patches. And there's one point on which I will insist quite a lot. So let's start with the global structure of the method. So like in the 2D inpainting case, so the video inpainting will be performed by analyzing the whole sequence. I don't know if you see the light blue color that represents the whole sequence as a spatial temporal cube. And then what we'll do is so then there's a smaller region that's the occluded part of that sequence. And in that occlusion, we'll look for a patch, a 3D patch, which will usually be of size 5 by 5 by 5. And that patch around pixel P will look for a correspondent in the non-occluded region, and this is the known region, via a shift map. And we will try, and this shift map will be optimized in a way that it minimizes patch correspondence energy. So we'll look for the shift map, which minimizes the VL2 distance between the patch we want to disocclude and one of the known patches. So this is really a very difficult problem to solve. It's a very large dimension. Each of these patches have a very large dimensionality, around 500 dimensions in the case of spatial temporal sequences. The energy is non-convex, so you really need some tools to treat such a large problem. So thanks to previous work that set up this problem in a theoretical framework, we know that we can safely use alternate convex minimization of this energy, so alternating on U and phi. And we, of course, use a coarse-to-fine multiscale algorithm in order to guide the algorithm to to a good local minimum. And there are other things that I'll talk about later. So about this alternate minimization is justified by an analogy that was established by Arias and collaborators of this energy with a relaxed energy, where for each patch we look for not for the best corresponding patch, but for a set of corresponding patches in at center of that pixels Q. So how many patches we will look for as a correspondence are regulated by this entropic term. So if the weight of this entropic term is large, we will distribute correspondences between many correspondences. And what he showed in this paper is that when h tends to 0, so the entropic term has less importance, then this energy, so the weights that are here tend to delta functions, or to a set of the delta functions, and we go back to a formulation like this. And this gives a more easy framework to show convergence results. And since we have convergence when h tends to 0 from this to this, then we know that we can safely use alternate minimization of this non-convex energy, but that is biconvex. It's convex on U and W. And here it's convex on U and phi. So this justifies this kind of algorithm where we alternatively minimize on phi, that gives the nearest neighbor search, and on U, and that gives video reconstruction of the sequence from this shift maps via aggregation of patches. And this is carried out in a multi-resolution scheme in order to help find good local minimum. So I said that the problem is difficult computationally, so we need really fast algorithms to search for good correspondences. So this was solved in many different ways. In the case of image Inpainting, one of the most successful ones was the patch match methods proposed by Barnes in 2009. In video Inpainting, surprisingly, the patch match had not been used before. The people used other techniques like KD trees that are good enough for accelerating search at dimension 10 or maybe 20, but not for dimension 500. So what we did was just extend the 2D patch match to the 3D case, and it really manages to accelerate a lot. Just to recall, the patch match is based on the piecewise constancy of the shift map. That means that once you find a correspondence of this point, then you will look around and see, well, maybe the points that are close to this point will have a similar shift map. And so it suggests that, and it will be tested, and if it provides a good enough correspondence, then it will be kept. Otherwise, you have a random search. So just adding this and a few other ingredients that we'll talk about later to this patch-based algorithm, managed to accelerate a lot the convergence of the algorithm and obtain as good results as a previous method by Granados, which was the reference at the time. So I'll show you the video. So there's one person that we want to remove here. And so what I show here is the inpainted sequence of both algorithms. So you see, qualitatively they are very similar, but in terms of running times, there's a big difference. So our algorithm is roughly 10 times faster than the other one. And this despite the fact that and it is of course much faster than the Wechsler's algorithm, which did just brute force search. In case of another aspect to be considered is that the method of Granados and collaborators, it is based on graph cuts, and to make the graph cuts algorithm tractable, you don't have to you shouldn't have lots of edges in your graph, and to avoid to have a too large number of edges, you need some kind of user interaction to guide the search regions. So to see roughly this person walking can be searched for in this area of the video. So you have to manually input that to guide the algorithm so that the graph cut is not lost with too many options. So, and this summarizes the running time. So you see it's faster, but it still takes a lot of time. So it takes something like 4 or 6 hours to run on this sequence. And still, this is more than 10 times faster. So that's why I say it's starting to become tractable, but there's a long way to go. Now, to obtain good results in terms of quality, an essential element is to take into account the nature of textures that we want to inpaint. And I'll show that on an example of this America. So my student is English, and he really liked this picture because he had fun of it. So we'll try to inpaint this region, so the bird. Okay. So, and this is what happens if we perform the method as I described until now, using just a Euclidean distance between patches. So you see that the bird will be smoothed out, and you really don't. So it's really smoothed out in the final version. So to correct that, you have to realize that the problem really is the distance that we're using to compare patches and to get similar patches. If you look at a single patch within the bird, that before occlusion, you realize that the correspondence, the corresponding patches in the whole image, they are distributed. A few of them on the bird, but most of them on the head, which has the same mean color, but not at all the same texture. So you really need to introduce some notion of high frequency in your distance to discriminate those cases. And what we did was very simple, and it was based on this theoretical observation. Imagine that you have an extreme texture that's made up of just white random noise. And your question is, you have another realization of the same texture, the same random noise with the same parameters, and then you have a flat image equal to the mean of mu, to the mean of that random texture. And you ask what patch is most similar to X, Y or Z. You can perform a simple calculation. You compute the distance from X to Y, the distance from X to Z. Then you take the expected value, taking into account this random model and the fact that these two are independent. And then you end up with 2n sigma square for this distance and n sigma square for this distance. That's a very simple calculation. It means that in most cases, so that's on average, so this distance is twice as large as this one, and on average the constant region will be preferred. So you have to have a lot of chance to find a realization of your white noise which is exactly the same as what you're looking for. You should look at a really very, very, very large region a lot of examples to have a chance to find a good correspondence which has exactly the same characteristics, more than just the deviation to the mean. So one way to go around that is to change the distance in a very simple way. So what you do is you compute the derivatives at the fine scale level. You take the mean of the derivative in the x direction and the y direction, and then you average that up to the level you're treating. And this will be an additional feature that will be used to compare patches in the L2 sense. Okay, so this is one of the features that are used and are added to the color information. And once you add that, you will see that the corresponding patch for this region, some of them will be in the hat, but as it was before. But when you change the distance, most of the correspondences will be in the right place. So you really improved the perceptual meaning of the distance you're using. So and this is the Inpainting with the standard Euclidean distance. That's a competing method which has the same problem, and this is what you obtain with the modified distance. So it's much better in terms perceptual terms. And this is the original one, so it's a bit far away. You can do the same thing in an experiment where you show that actually you can inpaint noise next to a flat region. So if you do it with the unmodified patch distance, the result what we will get is just you will propagate the flat region. And if you do it with the texture-aware distance, then you will really propagate, as you expect, realization of the white noise on one side and flat on the other side. Okay. So this is important when you have very complex scenes where you really want to, where there is a small texture, and even if it's dynamic, you don't want to smooth it out because it will look very differently. So this is the original video where we want to remove the boats. So this is what you get with the Euclidean distance. So you see that it's a little bit washed out here. You will need a little bit more contrast to see that. If you do it with the modified patch distance, then you see that well, it's more high frequency here. It's more plausible. Well, there are other examples like this. Another question which I will not have time to deal into is to the choice of how many levels you have to choose in your multi-scale criterion. In most cases, this is chosen in a very heuristic way. You can actually show that there's a value that you can compute the size of your occlusion, the number of levels to use in terms of the size of your occlusion, and this is due to a theoretical work that shows. Well, sorry, this is not working. That shows that if the occlusion is too large with respect to the scale, then you will not perform a model completion here. And up to a critical size, you will be able to do that. And that's the scale that we have to choose. Well, I show you one more result, and then I'll go to the perspectives. So this is the original video. For people who know Paris, they will recognize where it is. It's the Fontaine Saint-Michel. Or Châtelet. No, I have that. So, and the Inpainted version is this one. I really like this example because you actually manage to remove the person going in front while still keeping this water flowing in a natural way. So this water flowing was behind the person. And you managed to do this by copying and pasting in an intelligent way. Okay, so I skipped this result. Just, well, a few open issues. And when motion is very complex, so we're happy with the results, but there are still a few cases where it doesn't work very well. One of them is complex motions. The cases where the occlusion is very long in the temporal sense, then you can solve it by subsampling, but it doesn't work always. We don't have a systematic way to deal with that. And selecting the size of the patch is also critical. So I think that some of these issues could be solved by addressing more fundamental questions, like which are the more general discriminative features that we should use to be able to better discriminate dynamic textures and shapes. We can use motion features or true multi-scale criterion instead of using just a coarse to find a local minimum. The scattering transform proposed by Bruna and Mallar is also an interesting thing that could be integrated into this kind of scheme, because they provide the properties of that we're looking for. Actually, what we propose can be considered as a very simple particular case of the scattering transform. And then there's the problem that Inpainting, as I proposed, is really deterministic. So you really copy-paste complete regions. You don't have a random behavior. It would be interesting to switch to the generative Inpainting case, and this is starting to be demonstrated with success by Rad, Desaulniers, and Morel. And what's interesting, I'm excited about this because going this way produces better results by using conditional Gaussian simulation. But you need tools to learn and query those local Gaussian models in an effective way. And that's exactly what I've been doing with my student Guillemot. So I think there's a way to put both things together to build more powerful Inpainting and restoration algorithms. So that's it. You can go have a look at more data, see our poster here on another subject, and of course we have a PhD position. Don't hesitate to contact us if you have a student.
Thank you very much, Andreas. Can I ask you? I think it's actually one question actually regarding the generation of structures in terms of actually sort of removing that. In terms of what we saw from ARM here, how does that play actually into some of the work and some of the research that you were talking about there, Andreas?
It's kind of computational resources.
Yeah.
But the kind of computation we do is very different, because we don't have any 3D model of the scene. We don't even try to infer that. It's just cutting and pasting different parts of the video so that what comes out seems plausible. But we don't have a 3D model or any idea of whether this corresponds to a physical object. It's very different from the virtual reality scenarios where you start from the model, so you already have it, and you give it to possible motions. But you could envision doing things like learning motion from videos, from plain videos, not just market 3D videos, and putting them into the real-time 3D generators. So I don't know if many people do that.
it, it's difficult. It's a lot easier to just start with some 3D model and then move the cameras around. It is very hard to take just 2D image and do something that then makes it a believable 3D world. I mean, there's been lots of interesting research on this, and the sort of idea of sort of popping 3D models out of a 2D image is definitely a good start. But I can't see, in the short term, I can't see things like VR and games consoles for real time using anything other than rendering triangles in 3D. So you've got to get your model to that point to get it onto the GPU.
Gaming industry. I've got a question down here.
Yeah, it's a question for the first speaker. So most of the infilling type work takes patches from the current either image or video or something like that. I'm wondering, is there a possibility of actually creating a library of patches in advance, sort of offline, that might make it easier to do the filling? You can then do sort of indexing and pull it in. Maybe you have to do some shading adjustment or chromaticity adjustment or something like that. But
it could be a good idea. I don't know if many people doing that. I know many people doing this kind of thing for image restoration, which is kind of much more controlled. When you're doing Inpainting, you rather rely on the nearby information in order to fill in information that really melts with the surroundings. It could be done with an external library. I know I don't know of anybody having tried to do that, but sorry.
Hayes and Efros, they do.
They do that.
Image lookup and then.
In an image setting. Okay.
I was thinking of like a database of little patches or something like that.
Yeah, it certainly works for more constrained restoration problems where you can really improve the restoration capability. And I've done work on that for doing super resolution, for instance, which is some kind of Inpainting. And in that case, you can collect images from whatever. So and then the problem is really to index all that information in a correct way, in a correct database that you can query and sample effectively. So
I'm just going to follow on that actually, which is imagine all the patches in the world. Yeah. So most of them are blank, right? They explore the color gamut of the world, and then a subset of them can include edges, and if you make it rotational invariant. So if you think through all the patches in the world, you're going to end up with a prior, which looks like piecewise constant or overlapping of piecewise constant regions. So I think there's something weird happens with these in-image things. The image is a better prior for itself than all the patches in the world. I don't know how to resolve it.
It certainly has to do with the metrics that we use to compare patches. So when you think of no-local means as a way of denoising, it was traditionally constrained to a nearby neighborhood because it just relies on Euclidean distance. And if you use patches that are very far away, then you smooth everything out, and because your distance is not reliable. If you really use distances that are aware about the shape of this manifold of patches at many different scales, then you could do something like that. And I think what the work of Zoran Weiss was a little bit in that sense, that they tried to build a library of Gaussian models for image patches, which is universal in a certain way. But well, the size is restricted, but it goes in that sense.